Okay, now we're ready to get into the more interesting part of organic chemistry, reactions. And we're going to start with reactions of alkenes and the stereochemistry of addition reactions. This is chapter 6. Now, before you begin this chapter, I want you to have out and ready two things. They're found in our files. You need to please have out your functional group notebook. Your first entries on your functional group notebook should be due at approximately the time that you do test 2. And these will include the reactions of chapter 6 and of chapter 7. And that should take us through number 16. So the first reactions due will be 1 through 16. And that will be at exam 2, which is this week. So if you keep out your functional group notebook ready, then you can fill in the requirements for the functional group notebook as we come across them in the video. The other thing that you should keep out and ready is this drawings for showing what the alkene, when the alkene reacts with the reagent given, what will the product be? So you can fill out both this and the functional group notebook together. You could even use the examples here as part of your functional group notebook. And one of the entries, it asks for a specific example of a reaction. So just keep that in mind and keep these two things out and ready so that you can fill them out as we go through the lecture. Okay. And then we have something for you to work on. Here's a practice quiz. Something that, and I would highly recommend that you go ahead and write out the answers to this and keep these answers in mind as we go forward. So what are the 3 things that identify a nucleophile? That's something that you should remember. It's either going to be a negative charge, a lone pair, or a pi bond for a nucleophile. What are the 3 things that identify an electrophile? A positive charge, a partial positive charge, or a incomplete octet. Then you should be able to take a reaction and identify the nucleophile, whether it's a bond or an atom, and identify the electrophilic atom in each step of the reaction. So we have an example reaction. And remember that one of the things you learned in the previous chapter is that arrows point from the nucleophile towards the electrophile. So if the nucleophile is a pi bond, a negative charge, or a lone pair, then, and the arrow is pointing from the nucleophile to the electrophile, would it be the sigma bond that the arrow on the left is pointing at for the first step, or would it be the pi bond that the arrow on the right is pointing out for the first step? And it would be the pi bond at the right. So that's our nucleophile. The pi bond. And then since we point from the nucleophile to the electrophile, the hydrogen is our electrophile, E+. For the second step of the reaction, the nucleophile must be a lone pair, a negative charge, or a pi bond. In this case, we should have an arrow pointing from a lone pair. So then this lone pair is the nucleophile, lone pair. And the electrophile, the arrow points at the electrophile. The electrophile can be a positive charge, a partial positive charge, or an octet. Here we have a positive charge, so that's our electrophile, E+, at that carbon. Then in the third step of the reaction, we have, again, another lone pair for our nuke. And for our electrophile, we have this partial positive hydrogen atom because the arrow is going to point at the electrophile. And that would give us all of the electrophiles and nucleophiles of our reaction defined. Okay, the mechanism of an electrophilic addition reaction. So all of the reactions most of the reaction we're going to be covering in this chapter are going to be electrophilic addition reactions. And we're going to start with a mechanism that we actually looked at in the last chapter, and that is the addition of HBr to a pi bond. So in general, for an electrophilic addition reaction, the first step of the reaction is going to be the slow step or the rate limiting step. And the second step of the reaction, the intermediate carbocation becoming final product, is going to be the fast step. So the slow step is formation of the carbocation, and the fast step is from carbocation to product. And you should note that the vinylic carbon, that from the reactant, we have two vinylic carbons. Those are the sp2 carbons of the pi bond. In the product, each of the vinylic carbons now has a new sigma bond to a new atom, and the pi bond is gone. So we can highlight our new sigma bonds. They are from carbon to bromine and carbon to hydrogen. Okay. Features that all electrophilic addition reactions have in common. Okay. So features that all electrophilic addition reactions have in common. They all have a pi bond that breaks. They all have an electrophile, and they all have a second nucleophile. And the electrophile and the second nucleophile are not necessarily in the same step of the reaction. In fact, they usually are not. So the electrophile is going to be seen in both, they're going to be two electrophiles and a pi bond that breaks and a nucleophile in the second step of the reaction. We're going to have two new sigma bonds. One of the new bonds will be to a nucleophile, and one of the new bonds will be to a electrophile. Okay, addition of hydrogen halides to pi bonds. Only strong halo acids, HBr, HI, and HCl, will add to a pi bond. And our electrophile is going to be H, and our new nucleophile that forms a bond is going to be Br. So what we're essentially doing is taking the H and the Br and adding hydrogen to one of the vinylic carbons and bromine to the other vinylic carbon. Now, of course, it can't be that easy. We're going to have rules about which carbon, if the carbons are not identical. So these two carbons, they have the same methyl groups. This is a symmetric molecule, so both of the vinylic carbons are equal. So one of the vinylic carbons gets hydrogen, the other one gets bromine. It doesn't matter which. But if the vinylic carbons are not equal, then that's going to have a different end result in the product. And we're going to get there eventually. All right, so when we draw out this reaction, and I think this is the first reaction on your functional group notebook. We go back over here, functional group notebook transformation, addition of HX to alkenes. So yes, HX is halo acid. This is the first entry in your functional group notebook. For the first, the pi bond adds hydrogen, and the bonding electrons between H and Br go to bromine. We have our intermediate step for our formed carbocation with the new bond to hydrogen at one of the vinylic carbons. And reacting with the bromide ion adds to the positive charge, and we get our final product. One of the vinylic carbons now has a hydrogen, the other now has a bromine. The same thing, the same general mechanism occurs when we have cyclohexene reacting with HI. We add hydrogen to one of the carbons and iodine to the other. Because it's a skeletal structure, we don't actually have to show the new bond to hydrogen. But it is there. This carbon, which once had only one bond to hydrogen, now has two hydrogens because it shows that it has a neutral charge. Okay, which sp2 carbon gets the hydrogen? This is actually going to matter, just as I mentioned. So we have to rank. What we do is when we do the first step of the reaction, it forms what we call a carbocation intermediate. And it turns out that some carbocation intermediates are better than others. The more carbon to hydrogen bond, the more carbon to carbon bonds from the positive carbon, the more stable the intermediate and the better the cation. So tertiary cation is better than a primary cation. So if we have hydrogen adding to the vinylic carbon that is disubstituted carbon, that will result in a primary cation. The other vinyl carbon, the one that didn't get the new bond, would become positively charged. Let me illustrate this with a highlight. So if the yellow carbon forms a new bond to hydrogen, then it becomes a primary carbo. Then we'll have, so we have green carbon and a yellow carbon. If the yellow carbon gets a new bond to hydrogen, then the green carbon becomes a primary carbocation. If the green carbon gets a new bond to hydrogen, then the yellow carbon becomes a carbocation. So this is all saying which one is forming a new bond to hydrogen. And let's go ahead and draw in that new bond to hydrogen. Showing that this is now a CH3 group and that the yellow carbon has a hydrogen in the other case. So if the yellow carbon forms this new bond to hydrogen, we get a green carbocation that's primary. If the green carbon forms a new bond to hydrogen, then the yellow carbon is a tertiary carbocation. Tertiary carbocations are better than primary carbocations. And in the second step of the reaction, the halide adds to the positively charged carbon. So that results in two possible products. That the chlorine adds to the tertiary carbon or the chlorine adds to the primary carbon. And it is the major product of this reaction is actually going to be the product that has the halogen bonded to the tertiary carbon. So what we're using to determine this is the relative stability of carbocations. A tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation, which is more stable than a methyl cation. So as the number of bonds to carbon, or the R groups, increase, the stability becomes higher and the carbocation is lower energy or better. So alkyl groups decrease the concentration of the positive charge on the carbon, and that is called hyperconjugation. What happens is that the hydrogen to carbon sigma bond can form what we call hyperconjugation, which almost looks like a pi bond. So this carbon to hydrogen bond is actually donating electron density into the empty p orbital that we get when we have a carbocation. And that stabilizes the carbocation. So the more carbons that this is bonded to, the more interactions of hyperconjugation we're going to have, because the more adjacent carbon to hydrogen bonds we have. So if you look at the bottom, I have listed it out. For a tertiary carbocation bonded to 3 methyl groups, we actually have 9 hyperconjugation interactions stabilizing the cation. For a secondary carbocation with two methyl groups, we have 6 hyperconjugation reactions stabilizing the carbocation, and that's what those red dots mean. That's 1 hyperconjugation reaction per red dot. For a ethyl cation, which is a primary carbocation, we only have 3 hyperconjugations stabilizing the cation. And the same thing for a propyl cation, only 3. These are both primary. And for a methyl cation, there are 0 hyperconjugation reactions. So the mechanism for hydrogen halide addition gives what we call a Markovnikov product. The Markovnikov product has the higher priority group bonding to the more substituted carbon. Okay, that's what Markovnikov means, and you're going to hear Markovnikov used a lot. But Markovnikov is going to have the higher priority group bonding to the more substituted carbon. So if you look at chlorine and hydrogen, which one is higher priority? Which one has a higher atomic number? Chlorine. So chlorine bonds the carbon that has more carbon bonds. And you can, so they actually are showing the mechanism here, and you could use this mechanism for your mechanism on your functional group notebook if you desire. So here we have the pi bond reacting with hydrogen, the bond between H and Cl breaking. Then that gives us the tert-butyl cation preferred. Remember, because we've just said how the tert-butyl cation is more stable than the primary cation, we know that we don't use this bottom arrow, and they show that with an X. It does not occur. So then our tertiary cation that we formed is now an electrophile, and that reacts with our negative chloride ion. So we have chloride lone pair going in an arrow to the positively charged carbon. And that gives us our final product of the tert-butyl chloride. And so for key points for this reaction, one of the things that you would put is that it's a Markovnikov reaction, or that the hydrogen is going to bond to the carbon with more hydrogen atoms, and the halide is going to bond to the carbon with more carbon-to-carbon bonds. So we've written out the definitions for you. Markovnikov product, the highest priority new functional group will add to the vinylic carbon with the most carbon-to-carbon bonds. And then we have another type of reaction product called the anti-Markovnikov product. And in this product, the highest priority new functional group will add to the vinylic carbon with the fewest carbon-to-carbon bonds. And in this chapter, all but one of our reactions is going to form the Markovnikov product, and I'll be very clear to point out which reaction gives the anti-Markovnikov product. Okay. So the relative rates of carbocation formation determine the relative amounts of product. The more substituted your carbocation will be, the faster the reaction will occur. So only the product with the most stable carbocation forms if the other carbocation will be particularly unstable. Like if your only options are tertiary and a primary carbocation, only the tertiary forms. And so that's what they're showing here. The only product formed was the product resulting from the tertiary cation, and I can show you a fast way to go from product to cation. If you are given the product and they're asked what the intermediate was, you can take this product that has a new halide bond, erase the halogen bond, and put a positive charge on the carbon in place of the halogen bond, and then you'll know what your carbocation intermediate was. Okay, so that should make it very clear to you one method of going from product to what the carbocation intermediate was. Okay, positive. So we have a tertiary carbocation that is formed, the product coming from the tertiary carbocation is made, but the product coming from the primary carbocation is not formed for this reaction. similar energies are going to result in similar structures. So for a reaction energy coordinate diagram, similar energies should result in similar structures. So if what this means is that if the reactant is closer in energy to the transition state, then the transition state is going to resemble the reactant. And if the product is closer in energy to the transition state, then the product is going to resemble the transition state more closely. And so in an exergonic reaction, the transition state resembles reactants. And in an endergonic reaction, the transition state resembles products. Remember, an endergonic reaction is a positive delta G. The only way that reactions that are endergonic can occur is to add energy to the reaction. That's something that you learned in Gen Chem. And one of the ways in which we add energy to a reaction in the lab is to do a reflux, as we did with the salicylic acid reaction.